There's a common misconception that this capacitor is really roughly the same thing as a battery. And I can see that confusion because after all, now we've seen that these capacitors are definitely devices that can be used to provide a source of electricity, a source of electrical current. But there's a big difference. Batteries maintain a steady voltage across their terminals as they're being used. So if we were to make a graph of the voltage this provides over its lifetime, it's just a steady flat line until the battery finally, I think, what do we say, the battery dies is the typical expression. When it dies, then suddenly the voltage drops off. But as long as it still has the ability to power, it powers things at a continuous voltage. The capacitor, the voltage drops off over time. If I could make a graph of voltage versus time as a capacitor powers any electrical device, I believe that graph would look something like this. So time t equals 0 is when we first complete the electrical circuit or maybe drop a switch somewhere in the circuit. And the voltage versus time, the electrical potential difference it provides across the terminals of whatever it's connected to, just fades away towards 0. It's exponential decay. Whereas a battery, like I say, it's just going to provide a steady voltage throughout its lifetime. So let me illustrate that with this circuit. Nope, what have I done? There it is. So the circuit has a battery we see here. I'm going to take a wire from the positive terminal, and that wire is going to run through a green light bulb. And then I don't have it connected yet, but if I wanted to, I could make the final connection to the positive terminal of the capacitor, and we would have a complete loop where electricity flows from the battery through the light bulb and also has to flow through a capacitor. Okay. Well, if I remove that, then this part of the circuit's broken open, and instead I can complete the circuit here. Now, if the capacitor then is fully charged, then when I connect the wire that attaches to the red light bulb, it'll glow. So I have essentially my green bulb is the charging bulb, and my red bulb is the discharging bulb. To save time and make it neater, we often don't really draw the components of the electrical circuit as they appear, but we make a schematic diagram for it. So here's the symbol for our battery. It happens to be a 6-volt battery in this case. And then we've got the light bulb, which is effectively a resistor. So I'll call that resistor number 1. That's my charging light bulb. That's my green light bulb. You see the capacitor. It's a polar capacitor, so I have to make sure I'm aligning the positive terminals and the negative terminals correctly. And then, yeah, I have the discharging bulb as well. Okay? So the battery is not included on the discharging loop of the circuit. The discharging bulb is only powered off of the capacitor. Okay. So I guess we have a two-way switch right here, right? Yeah. So let's see. First of all, I should make sure that I'm starting out with an empty capacitor. You never know when you pull a capacitor out of a drawer or you walk up to a circuit that's already been connected, whether or not that capacitor is storing charge. You can't see it, you can't smell it, you can't hear it, you can't taste it. So we could just piggyback this wire into here and then connect. And now if there were any charge in this capacitor, electricity would have flowed through this wire and neutralized the two conducting plates of this capacitor. All right, so we know we're starting with a uncharged capacitor. We'll keep our discharging wire on standby here. And then let's complete this circuit from the battery to the light bulb through the capacitor. We say all 3 elements are connected in series. And what we should see is the light bulb glows brightest at first, but then eventually fades out and goes dim and isn't glowing at all anymore. Now, why is that? Because the capacitor gets to a point where it's fully charged. And when it's fully charged, its electric potential difference matches that of the battery. And so there's no difference in electric potential from the positive terminal of the capacitor compared to the positive terminal of the battery. And without, both of these points are at high potential, but there's no difference in electric potential, and so the light bulb isn't glowing anymore. If I disconnect it and then reconnect it, it's still not going to glow. It hasn't changed. This capacitor still holds its charge. Now, if I disconnect it and use my discharging wire, I believe I've taken all that charge out of the capacitor. Let's see. Now, when I connect my charging light bulb a second time, this time it should glow again until the capacitor has a voltage that matches that of the battery. Okay? Now, if we disconnect and connect our discharging portion of the circuit, then in the same manner, the red light bulb is going to glow, or orange light bulb, I guess it is, and it'll continue to glow until the capacitor is fully discharged. And you see, that gives us the graph that I suggested, that the voltage is decaying towards zero as time goes by. So that gives another practical application for capacitors in electrical circuits. When capacitors are combined with resistors, there's a certain time delay for which the electricity fades away to being practically zero value. Now it depends on what's the exact value of the capacitance and what's the exact value of the resistance. But in any case, that's a second function to capacitors in practical application. They're not just there to deliver a sudden burst of charge when you need it, but when the current is run through a device that resists the flow of electricity to some degree, the time delay that it takes can be controlled by the combination of how much resistance and how much capacitance. Pretty neat.